you changed it.
Well, content is the same.
Quantum dynamics and environments, the BAF methods.
Yes. So actually the BAF methods I added because I sort of liked Michael's remark during his introduction to the conference, because I think indeed the BAF does matter. So since a year I'm actually at the University of Ulm. Before that I was at Imperial College, and I'm still 10% here and 90% there, in fact. So, right. So I would like to make some remarks about two aspects. So one is I'd like to, in a way, I'd like to break a lance for the idea that we would like to really deconstruct elementary building blocks of dynamics, see how much each of them contributes, and use this maybe for optimization. That's one thing that I would like to briefly touch upon. And as a consequence of that, I will see that the treatment of the environment may actually be have to be, refined, let's say. And so what I would like to then do is I would like to explain you a different approach towards the modeling of the system-environment interaction that is non-perturbative and has potentially certain other advantages, and it's sort of a combination of quantum information and condensed matter and mathematical methods that we brought together to make this to work. And I'd like to present this, and then we can see whether this is actually potentially useful or not. Okay. So, well, what are we concerned with? Well, of course I cannot give a particularly good introduction to the physics or the chemistry of the FMO complex. We have seen a very nice introduction by Greg Engel about that. So I take the quantum information approach to that, so that's the community I originally come from, or quantum optics, to idealize systems a little bit. Actually, not only a little bit, quite a bit. And see what the dynamics of those idealized systems is, try and derive some sort of simple principles maybe, and then stick all of this together again, putting more and more realism into the game, but having an understanding of what I put together and how it fits together. So that would be my approach in that. And so one way of doing that is, so we take the FMO complex, we abstract it a little bit into having 7 sides, which seems to be a reasonable thing to do. We'll have interactions, hopping interactions between those sides, we will have noise, we will have maybe loss, which is on a time scale of many times a nanosecond or so. We have transfer into a reaction center, and we want to know what happens when from the antenna some excitation comes into one side and it goes through this system. And you can just take these whole lot of equations here. They have a Hamiltonian part, you will have some dephasing part, interaction with the environment, and you can treat this to various degrees of approximation. So you could do a Lindblad treatment, or things like those, or you can go a little bit more precise. And you stick this on a computer and you see what happens. And then you see things like these, namely that if you treat if you treat the FMO as if it was completely isolated from the environment, then you will see that transport through that system is actually not particularly efficient. You will start here and you will sort of start to saturate off at 50% or so, and it rises a little bit further. But transport is somehow not very good if the system is purely quantum coherent. What you then see is, well, obviously that's not what experimentalists have measured, and therefore there's something missing, and that would be in fact the noise. So dephasing noise here does actually help you quite a bit, and it drives up the efficiency quite considerably, so that in the end it is almost, well, 95, 98, 99% efficient to transfer if the noise is at the right level. And so then you can say, okay, why is that? So initially we were sort of thought, this may be a little bit surprising, so we wanted to know what are actually exactly the underlying mechanisms. And when you ask some people will tell you this is obvious, this is completely obvious. You take the Hamiltonian, you go to the epsilon basis, meaning you diagonalize the Hamiltonian, and then there's no dynamics, so you need noise to have some dynamics in the system, and therefore you have this noise assistance. And in a way that's true. However, you could also then ask, so why do these excitons, for example, have a particular structure, like they have small overlap, the incoming state will have a certain overlap with some excitons, which have a small overlap with the site that is connected to the sink. Why is that? Where is this coming from dynamically? Do you always want to just have to say, let's diagonalize the entire Hamiltonian, we get out the excitons and that's it? Or do we also want to understand why do the excitons have the structure that they have? And so for that it might be useful to take the view of, I mean, to me this is, let's say, a bit sort of the view of, here's a clock, and so it's made up of all sorts of little, I mean, you know, components. And in one way we can say, sure, I mean, the clock works, I mean, it turns the digits and it shows you the time, and it does this somehow by internally having a drive, and then there are wheels and they fit into each other somehow. Or you can say, okay, that's certainly what kids would do, let's take this into pieces and try to understand how the pieces interlink. Right? And in a way, if you do this and you understand how this works, then you can go from a watch of this type, which is a relatively simple, cheap watch. I mean, I googled quickly cheap watch and I got this. And you might be able to construct then something much nicer, like this, which is, I mean, a clock. That is, well, they even call it chronograph. It costs more than our annual salary. So these are very, very well done clocks. They're very precise and all these things. So you might be able to take the pieces, you first take something apart, you see what is relevant, what is not relevant, what is important, how does it contribute, then put it together in maybe an optimized way. And this is a way that certainly we are pursuing in our group, but also Alana's Guru follows this philosophy. And also I think you will hear more of this, I think, in 2 days' time, when Janju Kao will also speak about that, how you can take these ideas and put them together and try and optimize networks. So there's sort of several people that try to go along this route. So, and of course, I mean, there are many contributions to this dynamics, and in a way, I would say each of these contributions is probably known in one way or the other. Yeah? So there's no doubt that we know, for example, that if you have two levels and they are interacting coherently, the lines may split up, and you may, for example, shift energies. Resonant energy levels by you having a coherent interaction. And that can be useful for you to, for example, allow yourself to absorb a broader spectrum of light, or internally in the transfer process it might be good for you because you shift an energy level closer to a different one. It might also, of course, have the effect that you shift another energy level further away, and this can be bad for your transport. And so you have to see in which situations it's good for you, when it is bad. The same is true also, I mean, you can have coherence and interference effects, which actually may stop the propagation of energy through the system. So you can have destructive interference where there are states that just don't evolve in time. Okay? And that would be a particular example that actually can play a role in networks, or does play a role, an important role in networks, where you feed in energy in one site. One specific site. And that seems to be the case in the FMO complex, for example. And I just want to briefly mention this in a little bit more detail. So take a very, very simplified model now. Yeah? This is super simple. It's just there to illuminate the basic effect. So you have here two sides, and they're both coupled to a third side with the same strength, and that one decays into the reaction center. And now if you imagine you would prepare sort of an antisymmetric superposition of an excitation being here or here. Then, well, I mean, it's very easy to see. What will happen here is that nothing happens. You have destructive interference of transition amplitudes. This state just stays up here and never goes here, and therefore you don't have transport in your reaction center. So of course you don't prepare this initially such a state. What happens rather is that you might come from the antenna complex, you stick in an excitation into this side, and then you see what the time evolution is. So let's do this. So we have here an initial state where actually the excitation starts in the right-hand side here. And now you see that in the course of the time evolution in this network, 50% of the population will get stuck, okay, by destructive interference, for example. So if here, you can write this simply as an antisymmetric superposition plus a symmetric superposition. This one actually has enhanced transport, it's faster, and this one is slower. And so what will happen is that this one goes very quickly to the reaction center, and the other one just stays where it is. Okay? And now you can see also how noise can help you. Noise will destroy or inhibit interference, And what it will do is, therefore, it can help you to make the state that seems to be trapped with no noise to propagate, while, of course, we have to make a sacrifice, because the good coherence, the one with the positive superposition, this state will be slowed down a bit. But the gain is of course, is there, because I have 50% that just doesn't propagate. So, and we have 50% that propagates very fast. So I think it's a good idea, actually, to perturb coherence a bit, so maybe make this one propagate half as fast, but this one also propagating a lot faster, maybe at the same speed. And the net effect is that you have a gain if there is a good separation of timescales, namely this slowing down, this sacrifice that you're doing, is not so big that actually the excitation, that your overall propagation is not slower than a nanosecond or so, right? Where you have really the energy loss. So you can sacrifice something, and in the end, enhance your efficiency of transport a lot. But of course, it will become a little bit slower. So you can see that noise is certainly a useful thing. And so this is just one example where you can take the dynamics, you break it down into little pieces, you understand how the noise is interfering with these things in a positive way, or sometimes actually in a negative way. And so you can have here all these examples. So this is, this would be destruction of, inhibition of destructive interference. Here you would have another effect of noise. If you shift an energy level out of resonance, then noise can actually help you to still bridge this energy gap that you have by just having two levels that are sort of have a separation. If you have sort of level fluctuations, then they fluctuate up and down, and occasionally they become very close, and so you have still transitions. So again, noise can help you, but of course it may, in other parts of the network, it may slow down the transport. So in the end, you will have all these contributions, and you will want to see what is the optimal noise level, how can I choose this, how can I maybe optimize the structure of this network to get the best transport in a particular given situation, for example, for a given noise level. So this is, okay, I could have shown this. I mean, we have analyzed this for the FMO complex to see what the contributions are, and the next step would, of course, be to optimize configurations, maybe nanostructures and these sort of things following such principles. And you will hear more about this from John Jokal in today's time. Right. Of course, so we have an interaction of noise with the system, and it can be beneficial. But it actually depends on the properties of noise, whether it is beneficial or not. So, for example, if you have here this trapped state, so this antisymmetric superposition, and now imagine you have noise that has spatial correlations in a way. So these transition amplitudes here, for example, could change sign occasionally, or change in any way, but if they are changing in a perfectly correlated way, then actually noise will not release this state and make it propagate. It will always suffer from this destructive interference. If, however, the fluctuations are anticorrelated, then it will do this particularly efficiently. And so these properties of the environment are actually important. And we have also, earlier today, we have already seen examples where temporal correlations may actually have an effect, or, I mean, may affect the way in which the environment interacts with the system. Okay? And so we certainly need to understand a little bit better properties of the environment. And there's another point why one may want to look more closely at more refined methods for treating system-environment interactions. And it's the following. I mean, when you start, usually you take some sort of Redfield equation approach or Limpard equation approach. You get your answers out, and then you get, for example, that you have sort of noise might help you in the improved transport. It goes over a plateau, and then when the noise is too strong, it goes down again. And there's this plateau. And then you ask yourself, where is it, roughly? And then you find that this plateau is actually in a place where certainly the system-environment interaction cannot be treated perturbatively anymore. It's actually too strong for that. So therefore, you have to remember that actually you started this analysis, or we started this analysis, with methods that explicitly assume that the system-environment interaction is not too strong. You can do some perturbative approaches, and derive such equations. So actually now you should have go back, refine this description, and see, A, is this maximum still there? Well, almost certainly it's going to be there, we understand that quite well. But maybe how narrow it is, where is exactly its position, and all these sort of things. And they may actually affect, in the end, the efficiency for a given experimental, biophysical system or so, quite a bit, because it might be that nature has put the noise level here, but our calculation shows that the optimum would be here. So we have to understand these things a bit better. And that's why we started to think of methods that allow us to treat the system-environment interactions in a non-perturbative way. And we wanted to have a certain number of properties for these methods. Okay? And so one is, of course, it should be efficient. So, I can always say I can take the system and the environment, I write down a large Hamiltonian, and I try to simulate that, and if I would do this, I could only treat 1 or 2 bath modes or so, and I would have a huge problem doing anything more complicated. So I need to find an efficient method where I certainly have to introduce some approximations, and I have to introduce them in a clever way, such that I gain a lot in efficiency, but I don't lose too much of the description, the properties of the system. And in fact, I would like to do this in a way, the method that I present to you will achieve this in a way that not only, well, I introduce a small error, but I actually can give you bounds on its size. So in the end, I want to have a method that gives you an answer at the end. It says 3 for some quantity. And in addition, it tells you the true answer lies in the interval from 2.9 to 3.1. So this is what I would like to have. Okay? And then I would like to have also the ability, of course, to increase this efficiency more and more. Furthermore, it should be versatile, because now I do not just want to take an idealized spectral density like an ohmic spectral density or so. I would like to be able to tell an experimentalist, give me the spectral density you believe is relevant here. Maybe it has some sharp modes in it, maybe it is going up and down like that. And I would like to be able to take this spectral density, put it into the machinery here, and simulate the dynamics of the system with these desired properties. And it turns out the way we do this gives you another little added benefit. It keeps actually track of the dynamics of the bath. So you can actually also ask questions about the state of the bath, if you like. So, yeah. So this is, oops. Right. So the approach that we are taking, I draw this in the following way. So this is here one side of, let's say, a dimer in this case, but you can also do this for more sides. Now you have here a side of the dimer, and it interacts with an environment that we model like a spin boson model, for example. So you have harmonic oscillators in the environment, and they are coupled to the central system, and this is quantified and described by the spectral density of the environment. And the problem here is, if you would just take this, of course you could say this is an exact description, that's great. But the problem is that if I want to describe this now numerically, I have a big problem, because the system evolution will start, and then all these oscillators will be excited, and there will really be strong delocalization here. So you will need, if you write down the wave function of that system, you will require a large number of probability amplitudes to describe this system accurately. In fact, it grows exponentially with a number of environment modes. Okay? So that's problematic for a simulation, because this is just not efficient. So you somehow, this is actually a question about managing delocalization, or actually managing entanglement in the system in a way that makes it amenable to a numerical description. In condensed matter physics, people have developed methods that do this very nicely, actually, in one-dimensional settings. These methods are called DMR, density matrix normalization group, and there are time-dependent versions of that. And what you there have is, you would have a system, and it would be coupled to a chain of harmonic oscillators, for example, and this could somehow also model your environment. And what would happen is that here an excitation would be created in a chain, and then this side would interact with that side, its nearest neighbor interaction only, then this side interacts with that side. And so you hand down the excitation, and of course in this handing down process, correlations decrease with distance. And if you have such a setting, then if you have distant sides, they will be almost independent, and therefore instead of having to describe all the probability amplitudes, it's enough to describe a product of amplitudes here and amplitudes here. And that reduces the complexity of the description. This works not always, but in this setting it actually turns out to work very well. And so this is something that we are going to use. I mean, in the end I could explain you maybe in more detail how this works, but it's not so relevant at the moment. The point is that you can find actually a description whereby you replace an exponential number of probability amplitudes by an expression that depends only on a number of real parameters that scales linearly in the number of environment modes. Okay? And it turns out that this is a very good description of that system. Okay. Of course, this is an approximate description. It's not exact anymore, and we have to keep track of this error. That will be important. But the first thing is, you can say, but we are not in this situation. The environment is not a one-dimensional chain. So you actually first have to find a way of transforming this setting onto that one. And you have to do this in a stable way. I mean, so you can find, in fact, recursion relations. And this was known already, actually Wilson started this. But when you look at his way of doing this and you try to do this for many, many bath modes, you will see that this is actually not numerically stable. And so you have to actually think a lot harder how to make this transformation from here to here. And there is a trick. You can actually transfer this to a problem from mathematics concerning orthogonal polynomials. And this is something that people have studied since 100 years. And they have invented, they've found probably almost everything that there is to be found there, including stable algorithms for doing this transformation, and in many, many cases, analytical solutions. So for many spectral densities, I don't even need to do a numerics. I just write down the solution for you for this transformation. Analytical.
Is it essential that the oscillator couples to just one side, or can it couple to several?
So
given
here or
oscillator,
here?
first on that side, and then with the
Okay.
consequence.
So here it is. So if you would have coupling between those here, for example.
No, I mean, this oscillator, can it couple to both sides?
Then it gets a bit harder. So this, I will come to this at the end. Yes, but one has to make a lot more effort, and it's not clear how to do this efficiently. I mean, possible is everything, but efficiently is really the big question here. And that is harder. I mean, we are working on a few methods for that, and we want to find out whether they are efficient in the sense polynomial versus exponential. But that's not completely clear. That's one of the challenges here. So, I mean, not everything is great here. Yeah? So this is one of the challenges that we have to address. Okay, but that's what we have. So now, how do you actually do this time evolution business? So here would be the parameter space, so to speak, that you can parameterize by this simplified description. So you start here, and you have sort of a product of let's say, matrices. Then you would make a time step, and it would of course lead you out of this manifold. Hilbert space is much bigger. So you would get a bigger matrix, and now you have to find the best approximation within this manifold to that state. Okay? And that's where, of course, the error comes in. But the great thing is, I can quantify that. In every time step, I can tell you what is the largest amount of error that I've made. Yeah? And then, because it's a linear system, I can just add them up, and at the end, that gives me a very conservative bound for the error on the system. Actually, it's an absolutely guaranteed one. Okay? So that's how this would work. And so now you can put this to work. And so we did this for simplicity also for the data. And we took a spectral density that was taken from a paper by Arlos and Renger, which has two components. One is sort of a, well, relatively smooth part, and it also had a sharp environmental mode in the system in addition. So this, actually, the presence of this sharp mode can make it a little bit more tricky for other methods to simulate that. Here the nice thing is I don't care actually, this description appears here, but then I have this transformation method, and for whatever spectral density you give me, I will get a linear chain, and I will get the coupling constants and the energy they are given to me. And then I can just turn the handle with the normal time dependent DMRG. And so we can do this simulation and we get graphs like that. We can start with a very weak system environment coupling, and then we increase and increase and increase the strength. So we go from a perturbative regime to a non-perturbative regime, and then to a regime where everything becomes almost classical. And so you can really tune through this, starting with weak oscillations. And I mean, so first you can get very strong oscillations where this one mode plays a big role, and then these oscillations are pushed down, and eventually also the dynamics will become very simple when the noise becomes very strong, or the system environment coupling. And so this is, I mean, here actually we really made an effort. So the error bars here are actually as thick as the lines, so to speak. So I mean, I couldn't even give you error bars, nearly none. And it should just serve as an example that you can actually really take a spectral density with smooth and sharp features, and you can treat the system non-perturbatively. And you can get answers out. And here, if we would want to know, we could also give answers about what is the state of the environment. So we could actually ask questions like, if you were to be able to start the environment in a particular state, and the system, how would this interact with each other? What would happen? So we could think of experiments even sort of trying to shape a particular wave packet in the environment and see what will happen. These sort of things become possible with at least from a theoretical point of view. And what will happen in this transformation actually is generically the following. So you would have one side and you have this chain. So at the beginning, you would actually have quite non-trivial coupling strengths, so that the energies, I mean, they could go up or down, and the nearest neighbor coupling would also sort of change in strength. And then, if you go further away, actually what you generically observe, you can even prove this, the chain that you get is one that becomes more and more translation invariant homogeneous. So the side energies and the nearest neighbor couplings become position independent. And they will actually have a particular ratio that is such that this remaining part of this chain is particularly good for transporting excitations away. So the picture that you get is all the sort of interesting structure and non-Markovian behavior of the environment is encoded in the first part of that chain. And the rest is really only there to ensure that you have eventually irreversibility. So excitation goes in the first part of the path, it jumps back and forth, comes back into the system maybe, wobbles back. And every time a part goes into the farther part, into these parts of the chain that are farther away, and that propagates to infinity. And in that way, you see also how irreversibility emerges here. It gives you a nice pictorial picture, while maybe in the original spin boson model it's not so clear how this happens. Okay? And of course, this allows you also to achieve numerical and also analytical approximations to the dynamics, because you can just decide that actually I can cut off the chain at a certain point, and the farther away I make this cutoff, the more precisely I model the dynamics of the system. And I can just take the chain, and at the end, so I cut it off, and I put a bucket here, so to speak, so an irreversible decay into the Markovian environment, and in that way make the numerical simulations more efficient, but at the expense of introducing additional small errors. That actually, those ones we wouldn't have under control quite so well. Right, so that's the summary. So here, I mean, this is a method that scales linearly. I mean, the computational effort scales linearly in the number of bath modes that you would have. And so we can do this with, I mean, 1,000 bath modes or something like that, or even more. It works for arbitrary spectral densities, actually. And in fact, I mean, the way I always present it is sort of you discretize the bath, but actually you can start from the continuous description of the bath and make a mapping, which is also an advantage of this transformation. This we only managed once we had the mathematics understood. The results come with guaranteed error bars, so that might be useful. The plots that I showed you actually were at 0 temperature. I have a diploma student who has just finished writing the code for arbitrary temperature, and he's testing it now. So that's also great. So in principle, you can do this for arbitrary temperature. Now, I have to be honest. So there are current weaknesses. So one is, actually the computational effort grows with increasing temperature. That's not surprising because the amount of environment modes that you will have to take into account and the excitation of them will grow with increasing temperature, and you have to keep track of that in this method. So that might be, that could be a problem. And so in a way we are coming from the bottom, and other methods, like for example the path integral methods, they come sort of more from the top. They work particularly well for higher temperatures, and they get a bit more challenging for lower temperatures. And it could well be that there's somewhere a crossover where we will start to lose and path integral wins, or the other way around. And the other thing is that correlations, spatial quantum correlations between paths, it's not so easy to treat. So this was essentially your question: if an oscillator from one path actually couples to a different site, that would lead to quantum correlations in the environment, and there we have, we still have to have, or we have to think a bit harder how to do this efficiently. Classical correlations could be done. You could just fluctuate the energies of different environment sites by a classical random process that has some correlations, and that would be a way to mimic at least some spatial correlations in the system that we can do. Well, so future goals. So one thing is we would like to continue to look at sort of design principles and deconstructing, so taking apart the watch, look at its pieces and understand how it works, so to speak, and then maybe use it for optimized nanostructures. And the other thing is, I think, well, we want to certainly continue to develop this numerical approach, but we would also quite like to compare it to other methods. I do not want to claim that this is the holy grail and it solves everything. I'm sure that every method has its range of applicability where it is the best. And it would be good to find out where these ranges are, so that we can in the end apply the best method for a specific setting. Okay, and that's the group that does a lot of the work. Okay, thank you.
Thank you. Questions, please?
Yeah, okay, now, sorry.
Can you also treat time-dependent driving?
Yes. That's completely straightforward in this setting. It's just a time-dependent Hamiltonian. You would anyway do the evolution goes via a, whatever, fourth order Coulthard effectively, and then putting time independence in is not a problem.
You've shown that you can transform this spin boson problem to a linear chain, by which I suspect that you've also shown that you can transform everything into a Brownian oscillator problem. Because I think that, can't you write it as a one oscillator interacting with lots of other oscillators?
Well, yes, but that's not the same as a Brownian oscillator.
Well,
because
it actually is. For not that version that we sort of blindly use in our papers, but in fact, this type of system where you have, let's say, electronic stuff, one oscillator, and that one coupled to a whole bath.
Yes.
That's what's Brownian oscillator, and that if you can transform it there and back, then
yeah, sure. I can do that, but that doesn't necessarily help you, because then all the complexity in the spectral density is still in this whole lot of other oscillators that you have there, and then you would either have to make approximate descriptions of that, where you don't know the error very well, or you have to continue this decomposition and sort of go step by step. Yeah, and actually, in a way, Wilson did it like that. He had sort of a recursive relation where he subsequently had one oscillator and the rest, and two oscillators and the rest, and three oscillators and the rest.
Yeah, I'm sure that you can't, with the Brownian oscillator model, you can only go to like second order interaction between system path and nothing better.
Exactly.
So you can do much better.
Yes, I can. This is non-perturbative, really.
But it kind of goes back to one of the questions that we had here, whether like these models with one mode coupled to a path, whether they are fine or not. You basically show that they're equivalent to the whole spectrum.
Yes. This is another thing. In the end, we have here. We have biological sort of complexes or so, they interact with an environment. And now we can make different levels of descriptions. We can do just a simple, second order perturbation theory approach, and you will get some answers. You can get much more fancy things like, path integrals or this, or hierarchy method or so. Then the question is, how much do we actually gain by that? So it might well be that for most quantities, it's perfectly enough to do a sort of second order perturbation theory approach, and you get roughly the right transfer rates and other kinds of efficiencies. And this will only ever give you a tiny, tiny improvement of the description, maybe at very short time scales. It's not clear. But you have to do it once to make it really rigorous and carefully and with error bars and everything. And then you can judge, okay, so this doesn't make a huge difference, and it's much better to go to simplified models like the Brownian harmonic oscillator or something like that. So that might also be a useful thing here simply in the end, that it just teaches you that there's not much point, and it's just a nice mathematical exercise. But we'll see.
This model of harmonic bath, how important are the quantum? How is it the quantum nature of the bath?
This is a quantum mechanical bath.
No, I know. I asked how important it is. Is there really a difference between using a quantum bath and a classical bath when you use a harmonic?
Well, what do you mean by a classical bath exactly? You mean a classical random process that fluctuates your energy levels. Well, how big a difference that makes?
Are there inherent quantum bath effects in this calculation?
Well, yes. There will be a lot of quantum correlations that will be developed. How important, however, they are in the end, really for the dynamics, that I don't know yet. We have to, and the point here is also, now we have gotten rid of most of the approximations. Now we can really say, here's a classical model, here's the exact quantum model, so to speak. We can compare and see, and whatever difference we see will be really down to quantum versus classical environment, and not some approximations here. Yes. This is really, but I cannot answer your question yet because we still have to do these things.
The drawings with respect to the form of the system bars couplings, say nonlinear bars couplings x squared or x cubic.
That
so we have the mapping.
This will be more tricky, I think. At the moment we just assume that it's some kind of linear coupling. The problem is that at present this transformation from the star-like configuration to the line, that really works. We have figured this out properly only for linear coupling, linear type. But it can be, it can be anything linear in the system, and any operator, anything linear in the environment, and any operator in the system is allowed.
Yeah.
But an x cubed or something like that, that's in the environment. That's going to be
usually it's the other way around. In the system, you're linear, and
right.
bars you might have several modes.
So I don't want to rule out that it might be possible, but we would have to think again, because there are some structural issues that went into this transformation for that.
So the high temperature gas become more classical. Why the more difficult approach?
Because it's true, it becomes more classical, and you would observe this here as well. But let's say if we apply this method without further thinking, so we have it, then what higher temperature means is that each of these environment oscillators will, of course, start out in some thermal state. And the higher the temperature, the more levels will be populated. And so the more levels will play a role in the dynamics, and we have to follow that dynamics, so we have to take into account more and more energy levels. And that makes it, of course, less efficient. There might be ways of transforming away some of these things and maybe restrict the number of energy levels. There are also adaptive basis methods in DMRG that may also allow you to make more clever choices. But let's say I would like to be conservative about this method, so at the moment I would say higher temperature makes it less efficient. Maybe in the end it is much better than we expect.
There was a question over there.
So actually, almost answered, but how about if the bath itself is harmonic?
Then again,
The same as
it's the same problem. So well, I mean, I understand it's not only if the coupling to the bath is anharmonic, if the bath is also anharmonic, you suffer also problems with this transformation. That's the same thing. If you manage in some way to transform from the star configuration to the line, and there is some unharmonicities in the line, that's not a problem for the simulation method. So you could stick this in afterwards and to try and see what unharmonicities might do in this line setting. And that goes through straightforwardly. There's no problem with that. But the transformation from one setting to the other, so how these two relate to each other, this would be the problem.
What about a spin bath, when you have spin 1/2 systems instead of harmonic oscillator?
It's a bit harder. You can do fermions in the same way. So if you really have fermionic anti-commutation relations, then everything goes in exactly the same way. If it's true spins, you have to. It's more effort, and we have to introduce some approximations basically, and then it still is fine in a way, but we cannot give you these guaranteed error bounds because these approximations we don't have fully under control. We don't know how big an error they introduce. But in principle, you can still. I mean, you can always take something that is a star configuration, map it onto the linear line, and you have to try and find this transformation, and sometimes you have to do some additional approximations.
So isn't it more efficient to just do the NRG, the Wilson NRG for this kind of chase? I mean,
yeah, but this is much better than time dependence.
Okay,
yeah,
because
this
of the
is
time
really,
dependence.
yeah.
So,
and actually, this is a question we also asked ourselves. So there are papers by Bullard
right.
that exactly
do energy.
Exactly, they do energy, and we at the moment we use this method to try and reproduce his results or see whether we can actually do this better. And it turns out that actually probably the limiting factor are more like finite size effects for this, in our case at least.
Or is there a mathematical reason why this is sort of superior? So these matrix products, the moves.
Well, I mean, this is certainly ideally adapted for time evolution. I mean, there is certainly no doubt. I mean, I'm not quite. I'm not sure whether I can answer this question in a way that I would still agree with in 10 minutes time. I'm not sure. But okay, maybe one thing I can say. One can actually. I mean, so matrix product states. You can very well justify why this will be efficient here. Yeah. So you can show, it's not a completely rigorous proof, but you can show that the correlations in the chain will remain small, and that's a precondition for matrix product states to work very well, and that you can show.
Maybe a question along these lines. There are few methods out there that you can treat this kind of systems non-perturbatively. There's a Reinholz path integral approach, there is hierarchical methods of Tanimura or multidimensional time-dependent Hartree. So where would you see the place of this method? What is the niche? I mean, how does it scale? I mean, what is the advantage compared to these other methods?
Okay, so now I have to, you're challenging me to say bad things about other methods. Let's say, I mean, okay, so this works, for example, at low temperatures. This works very nicely. I think this is perhaps more challenging for path integral methods. That's a fair statement. Generally, it works. It doesn't really care whether the paths, I mean, the correlation function in the bath, time correlation function in the bath is sort of falling off exponentially or like a power law. So it doesn't care about these things very much. So that has an advantage. Compared to the hierarchy method, I mean, the hierarchy method actually, if you try to implement it, I mean, the papers about this are mostly for a very specific spectral density, for which you can work out certain integrals, well, essentially exactly. And if you don't do that, you have, I think, a lot of numerical problems. Plus, in fact, your hierarchy, you have to go to greater and greater depth in the hierarchy, and it can actually, the computational effort can grow exponentially. And here, this scales linearly in this number of path nodes. So this is big advantage. And it works for any spectral density. I mean, I don't need to think. I mean, you give me a spectral density, I put it in the transformation program, and milliseconds later I get the coupling rates, and then I stick these into my DMRG, and whatever spectral density you give me, I can do that. So I don't need to think, which is a nice thing.
With respect to the system, I mean, can you treat a system with thousands of states?
Can I treat a system with 1,000? That okay, so.
2 is nice, but
Yeah, okay, I mean, we can do more than 2, yes? But 1,000, that is very difficult, but that is difficult, I think, for every method. If you have 1,000 sites, they're interconnected, and it's really quantum dynamics taking place there, you will have a spot of a problem. There are methods, actually. I mean, there are, well, multi-scale, MERA and PEPs and so on, methods that are being developed now in quantum information that might be able to treat such a setting. But there's a big might here. Yeah? I mean, so this is systems where everything interacts with everything, with variable strength and so on, are very hard to do, I think, for almost any method. So that's why, I mean, I think each method that is around will have problems with that.
But how do you scale this number of states? That was the question.
It depends on how your effective Hilbert space scales. So if your Hilbert space scale, if you have 7 sites, each of them is a qubit, and you allow yourself the 2 to the 7 dimensional Hilbert space, that's one thing. If you say, I restrict myself to the single excitation subspace, then I only have a 7-dimensional space. So it depends a bit on the dimensionality of the space.
And on this effective, is it still exponential, or is it?
Right. So in the single exciton state, it would be certainly linear in the dimension. So linear in the number of sites. But if there are more excitons, I mean, yeah, then anything can happen.
Okay, final question.
And how does it scale as the increase in duration of propagation? You have a very long time propagation.
Okay, so this is the nice thing here. So in general, such a method. So for example, there are cases, I can construct cases for you where this scales extremely badly with time dependence. So you just forget about all biology, take a linear chain, spin for an Ising model, for example. Then you prepare it in a product state and you switch on the interaction, nearest neighbor interaction. You use this method, DMRG, to integrate it in time. It will, the computational effort will grow exponentially in time. That can even be proven. If you do it without thinking, there are some tricks and you may then work on this, but this particular DMRG method would scale exponentially in time. The reason is the following. You have this chain. When you look at the entanglement in that system, you take a block of those spins and you look how entangled will they be with the rest of the chain. You will see that this entanglement grows in time until it's basically proportional to the length of the set. And that is problematic for this method. Now here this is different because you actually have a long chain and you shake it at one end only. So you put excitations into this system and they propagate through the chain, they propagate away. And so at each place in the chain the energy remains limited and the correlations also decay with distance. And that is a particularly convenient setting for this DMRG methods. And that's why it works reasonably well. And that's why, I mean, we haven't rigorously proven that it's linear in time or so, but it appears to be of that order. It's certainly polynomial in time.
Okay, let's thank him again.
Yep.
The next speaker is Stefan Olsen, President on the Hamiltonian Models for Environment with Responsive Fluorescence Lines.
It goes here if you want to use the remote. This one.